Yeah, so today I'm going to cover some basic concepts in AI development for games. And this is kind of like a setup talk for my talk tomorrow, which will cover a practical example of one of these AI models in the game that I'm working on at the moment with my team at a workshop called Tales of the Shire. All right. So what's AI? So I'm a former academic, so before I even say anything, I need to define what it is that I'm talking about and then kind of go into it. So here's your standard run-of-the-mill definition. AI, in its broadest sense, is very simply a collection of methods, techniques, and algorithms that enable computers to make intelligent decisions. But we're talking about game developments, and this is kind of how the broadest definition of AI applies to games. And there's two ways in which AI applies to games in also a broad way. The first one depends on the nature of the problem that you're trying to tackle, whether you're trying to make behaving agents for your game, whether you're using AI generation tools to create content for your game, or whether you're developing tools and pipelines for your team to use. Those can be AI supported as well. And then the second part of the question of how AI applies to game is the kind of solution that you use to tackle these problems. There can be machine learning in nature, and there's a lot of really exciting developments in that space. Or there can be symbolic, i.e. classical AI. I chose the word symbolic because it makes me feel better about the work that I do day in and day out, which is glorified conditional statements all over the show. So today, to refine kind of my focus for this talk, I'm going to be specifically talking about behaving engines in a game with symbolic AI solutions. And there's quite a lot, even in this more narrow focus, such as approaches to navigation, approaches to AI perception, behavior, and so on and so forth. But today I'm going to be specifically talking about how you will go about using various models to develop the behavior, the sort of actions that agents do in a game. So, to kind of summarize this definition portion of the talk, I'm revisiting the definition that I gave earlier on, what AI is in general for a very specific question of how do I go about, or what does it mean to go about developing behaviors for agents in games. And what I'm going to be talking about here is a collection of methods, techniques, and algorithms that enables agents to observe and represent the world in order to make intelligent decisions about their behavior. And I'm going to be talking about 3 different models, but they can kind of be summarized in this loop that happens time and time again every time that the agent needs to make a decision or think about starting to make a decision. The first phase being observation, which is when the agent detects things or about their environment that may influence their behavior. So that you might have an agent running around the world and there's some AI-friendly interactables around the world. So at this particular point, the agent will be scanning their environment and observing things that could potentially lead to their behavior changing in some way or form. Then there's an evaluation phase where the agent evaluates a whole bunch of options that they might have available to influence their behavior, if there's competing options available, or there might just be one. And then finally, the last step of this ever-repeating loop that is at the crux of a lot of game AI models is acting. So that is when the agent goes about doing the details of the selected action. And I kind of been alluding to this, but it's kind of important to know that this loop occurs time and time over and over at sample points is what I'm calling, and those can be on your game's update loop, or they can be event-based if you're worried about performance and all that kind of stuff. But the important thing here is that this happens at various sample points. All right, so the first model that I'm going to be talking about is finite state machines. Hopefully it's like one that a lot of you might have heard of. Finite state machines are comprised of mutually exclusive states with the active state controlling the behavior of the agent. Transitions between states and their associated conditions must be explicitly declared. So you must tell the agent, in order for you to enter this behavioral state, the day has to be sunny and you must have so-and-so equipped, and so on and so forth. During sample points, the conditions of all these transitions are evaluated, and then the state that has all of its conditions met is activated and enacted. So a finite state machine in its simplest form might look something like this, where you have a tree of connected states, and all these arrows represent possible transitions between states, and they would have transition conditions associated with them as well. This chap right here is Gary. He is going to be our guinea pig for today. And a little bit about Gary. He has it out for the player and would really, really like to kill the player. Gary can switch between attacking with a gun, which is a long-range attack, and a knife, which is a melee attack. And Gary, bless his heart, he's a devoted father of 4, and he would really like to live through any confrontation with the player. So based on his profile, these are the kind of behaviors that we might extrapolate as Gary having. He might idle when he has nothing else to do because either the player is not around or whatever. He might have a player detection behavior, an equip weapon behavior, knife attack, gun attack, and running away because, again, needs to make it home to the kids. Some of the properties that Gary might have based on his description are cone of vision to detect the player, an inventory to hold all his weapons, what weapon he currently has equipped, and health. All right. So this is what Gary's finite state machine might look like, starting from idle on the top left corner. Idle might transition into detecting the player if the player's within the cone of vision of the agent and Gary's health is high. And then from detecting the player, he might transition into an equipping weapon state after some animation. Like, say, for example, Gary goes, "There you are," oh, shake fist. That animation is done, and then he might transition into another behavioral state, such as equipping weapon. And a whole bunch of transitions that kind of encapsulates the behavior that I was describing earlier in his profile. And then along comes a game designer and says, "I would really like Gary to have a special attack when his health is below 25% but above 5%. And then you have to revisit your finite state machine and you realize that you're living in a living, breathing nightmare. And a way to overcome this with the finite state machine model is by using a hierarchical finite state machine model where you just nest state machines within each other, and then each sub-state machine might be an aspect of your agent's behavior, such as combat or being in dialogue and so on and so forth. And all of that ugly logic that I kind of showed earlier is now nested in a combat finite state machine. So out of sight, out of mind, nightmare lives in there. Finite state machines are great because they're intuitive. What you see is what you get. They're also very easy to set up. You don't have to be a level 10 programmer to make a finite state machine. You can make one with a couple of classes and away you go. That is, if you don't care about modularity, reusability, and architecture and all that kind of stuff, they're very beginner friendly. They can be very visual, which opens up a big opportunity for tooling and as programmers, enabling designers to curate these finer state machines with tools that we will provide alongside the system. But the downside is that complex agents can potentially have very nightmarish structures. So the next model that I'm going to talk about are behavior trees. Behavior tree is a hierarchical structure of nodes, kind of samey with the finite state machine, where instead of states you have nodes that control the flow of decision making of an agent. Observations about the world are mapped onto control nodes, while the resulting actions are defined in execution nodes. Basically, what that means is that all the sampling and the kind of data that the agent collects happens in control nodes, and then at the leaves, so the most extreme ends of the behavior tree, you have execution nodes which describe what the agent will do if the logic arrives at that particular leaf. At sample points, we use a tree traversal algorithm to navigate the tree and execute any viable actions that might come from that querying of the build, of a tree, I'm so sorry. So a very simple tree, binary tree might look something like this, where you have a start node, and then you have execution nodes that say, is this true or false, and then go down various branches until an execution node is hit, and then that action will be performed. So I might be telling you guys to suck eggs, but it's always useful for me at least, to have definitions to frame what it is that I'm trying to convey. So I just want to quickly run through some of the most common control nodes. You have sequence nodes, which evaluate and execute children left to right until one of them fails, and then the logic will the tree will be classed, the subtree will be classed as invalid. So an example here is that you might have a door sequence where the agent goes to the door, opens to the door, and goes through the door, and if for whatever reason, and it will go from left to right order, and if for whatever reason one of these actions cannot be executed, you go out of this tree. Then you have a selector node, which evaluates children from left to right again, skipping over any fails. So to expand our tree here, we might expand the open door action that we had earlier to have a bit more complexity, where the agent will test the door to see if it's locked, and if it isn't, thank you, it will try to open the door, but if it is locked, it might try to smash through the door, and then finally once the door is open, then it will go through it. Decorator nodes transform the result from the child nodes and return, so they return a success when there was actually a fail. So we can use decorator nodes to have a cooldown on this door sequence, so that the agent won't try to repetitively interact with the door and get stuck in this endless loop of opening the door, going through it, detecting that there's a door, and then going through the door again, and then back and forth forever until the end of time. This is what Gary's tree might look like. Again, all of his behaviors that I mentioned earlier are the leaf nodes, the most extreme nodes of the tree, and then you use control nodes to say which one of these behaviors, based on the current conditions of the game, can Gary do. Behavior trees, like finite state machines, are very intuitive. What you see, again, what you see is what you get. They're extremely popular in video game development. Unreal Engine comes with its own behavior tree tool out of the box, whereas you might have to source a third-party asset for Unity, or I'm not actually sure about Godot. Again, with finite state machines, they're very visual, so very leaning to tooling. And also, like finite state machines, complex agents can have very nightmarish structures. The last model that I want to talk about, and I'm going to race through this, is utility AI, which is where the agent scores available actions based on the current state of the world. The action with the highest score, utility value, at the sampling point will be performed, and it is completely transitionless. You might define an AI brain which has a bunch of these action classes that have get, score, start, update, and stop functions, and then at your sampling point, the AI brain will just score the actions, get score value, rank them, and then execute the one with the highest score. That's exactly what I just said. The evaluator here is the AI brain that I was talking about. Yep. All right, so what utility AI might look like for our friend Gary here is that when the player is out of the field of vision, the idle behavior will score highly because none of the other conditions for the other behaviors will be met. And then when the player gets into Gary's cone of vision, the utility value of the detection behavior might become really high if that is the first entry on a cooldown you might have in your algorithm logic. And say if Gary has very low HP, then at the next sampling point, they might choose to run away. So utility AI models are extremely powerful. They can result in very natural feeling agents, but they're not very visual based, or at least I haven't found a really easy designer-friendly way to tool them. And they might be too random for some use cases because you're essentially gambling on your value algorithms to turn the values that you might want in order to result in a specific rank of all the actions available to the agent. So which one do you choose? It depends. You might consider agent factors, such as the agent type. So in Tales of the Shire, we have a whole bunch of agents going from hobbits to animals, and we had a very serious conversation about which model we should use for our various agent types. We chose to use a different model for our simpler agents because they just needed to do a thing or repetition over and over again, as opposed to our more complex models which had like a cluster of systems that determined their behavior. You might also look into your project factors, such as your team composition, production targets, reusability, and stability. If you're an indie developer, kind of like going at it on your own, you might not want to consider something as complex as utility AI because you just want to get something out the door, and that's perfectly okay. If you're prone to chaos and a bad time, you can even do an unstructured AI model, which is a monolithic class that contains everything, and you live with the consequences of your choices. Not up to me. If you're working in a professional game development environment, things like reusability and scalability are really important to us. So making decisions about our AI model architecture that can support not only the game as it stands currently, but how it might expand in the future with DLC and all that kind of stuff is really important to consider as well when you go to choose what model you might want to implement. And then finally, developer factors might also play into your considerations, such as the skill level of the developer that might be implementing the systems, as well as motivation. And by motivation, I don't mean how many Fs you have. I more mean like if you're a student and you just want a game out the door to put in your portfolio, then spending 20 years on this beautiful scalable AI model is just not going to serve your purposes. But if you are like me, again, developer who wants to specialize in AI development, taking your time and making this piece of work, a demonstration of your skill is going to serve you well in your portfolio and your career. And that is it for me today. Before I hand the microphone over to questions, I just want to advertise some talks by some of my colleagues that are happening tomorrow. Like I said, I'm giving another talk on the AI model that I designed and implemented for Tales of the Shire tomorrow. My manager, Mark Barrett, is going to talk about our custom CI pipeline. Unfortunately, Stephen and Noni are not able to make it, so I'm going to skip that. And then Catherine, our game designer, is going to be giving us a terrific talk about how she uses diplomacy to wrangle the rest of the team in place. All right, thanks very much. Yes, there's 2 microphones.
Brilliant, so I can take one with me. Is this coming through? Wonderful. So the floor is open for questions. We've got about 5 minutes, so if anyone does have anything that they want to say, just put up your hand and I'll come racing over to you. Deafening silence.
Wow. Tough crowd.
Well, if there's nothing, if anything comes to you, feel free to come up to after the talk out there, everything like that. I should
say that I have a drop-in clinic at some time tomorrow. It's in the poster upstairs if you wanted to have a chat.